Welcome to this session. In this session, we will investigate the relationship between two binary variables and learn statistics to quantify the relationship. We look at two examples. First, we look at the relationship between ice cream consumption and weather conditions. Do people eat more ice cream on a sunny day? In scientific terms, we assume that when both variables are related, the ice cream consumption depends on the weather conditions. In the second example, we investigate if cardiovascular cases of family members is related to individual coronary heart disease risk. To learn about potential relationships between family history and coronary heart disease, we conduct a scientific study. To do so, we collect data. Let's imagine that we include all individuals of a population from a specific area in our study. We record if a close family member had a cardiovascular disease in the past and if an individual has a premature coronary heart condition. Then we construct a 2x2 contingency table to analyze our data. The inner cells show the number of individuals for each possible combination of both variables, the risk factor in the rows and the outcome in the columns. The margins show the number for each category. For example, 50,000 individuals were exposed to the risk factor opposed to 180,000 that were not. The total number of individuals in this region is about 230,000, which is a lot of data. Usually, in real-life research situations, we don't have data about every single subject in a population. But for this session, we pretend that we have the population data at our disposal. Now, look at the row margins of the table. There are more persons where the risk factor is absent, and that means when we want to quantify a relationship, we have to account for the imbalanced group sizes. We do so by considering each risk factor group individually. So let's compute the risks, which is just another word for probability in this context. We compute the risk for persons with a family history of cardiovascular conditions. In this group, 502 of 50,604 subjects have coronary heart disease. The CHD risk for exposed subjects is 0.01. Next, out of 180,000 subjects without a family case of cardiovascular disease, 532 suffer from CHD, although they are not exposed. To calculate the risk of the non-exposed, we repeat the procedure and get a risk of 0.0029. Now, risks have two nice features. First, they carry meaning. For example, we can understand what it means that the CHD risk for exposed people is 0.01, or more intuitively, 1%. The CHD risk for non-exposed individuals is only 0.0029, or about 0.3%. The second nice feature is that the risk accounts for the imbalanced group sizes, which means we can compare both risks. To quantify the relationship, we take the ratio of both risks, and then we obtain the relative risk. The relative risk is 3.37. That means that the risk of CHD is 3.37 times higher with exposed subjects than non-exposed. Based on this non-real-world example, we conclude that family history is associated with premature CHD, as the risk has more than tripled. A family history of cardiovascular disease is a risk factor for premature CHD. So what does that mean? If you had a family member with a cardiovascular disease, then you should have started to monitor your cardiovascular status to prevent premature CHD. There is a second way to assess the relationship between variables beside relative risks. It's called odds. Sometimes the odds are called chance. It's an alternative representation of probabilities, and it's a common measure in clinical research. Again, we calculate the odds for each risk group separately. We calculate the odds for the exposed group first. The odds is the number of exposed subjects with CHD relative to the number of exposed subjects without CHD. So to obtain the odds, we divide 502 by 50,102 and we obtain around 0.01. For the non-exposed group, the odds is 532 divided by 180,231, which is around 0.00295. Similar to risks, odds describe the chance of CHD. Keep in mind that they are not probabilities, but they are related concepts. Unfortunately, odds are less intuitive than risks, as risks are actually probabilities. In general, odds are thus harder to interpret. Humans lack a natural understanding of odds. But odds have important advantages too, as we will see. But now, appreciate that the odds account for the imbalanced group sizes and that we can compare odds for both groups directly. The odds of CHD is higher for individuals with family cases than for non-exposed subjects. To quantify the relationship with respect to the odds, we again calculate a ratio, this time the ratio of the odds, which is 0.01 divided by 0.0029. This odds ratio is 3.39. The odds of CHD are 3.39 times higher for exposed subjects than for non-exposed subjects. As we see, odds and probabilities, or risks, will lead to the same interpretation. Family history is a risk factor of CHD. What about ice cream? Is sunny weather a risk factor for having ice cream? On a sunny day, the individual risk or probability is about 3 times as high as on a non-sunny day, as indicated by the relative risk. The odds ratio indicates that the odds are about 4 times higher on a sunny day. Based on both statistics, risks and odds, we conclude that the weather condition is related with ice cream purchases. People tend to have ice cream on sunny days. So, the central takeaway message is that odds and risks describe the same concept in different terms. For both, we can calculate ratios to obtain information about the relationship between variables. And both statistics will lead to the same conclusion about a potential relationship. However, in general, we favor risks over odds as they are expressed in probabilities, which are more accessible for us as human beings. However, in some scenarios in clinical research, only odds ratios are available or odds ratios are favored by statistical methods. So there are actually interesting use cases for odds ratios, as we will see.